Okay, in this video, we're going to introduce the second coordinate system we'll study in this section, known as spherical coordinates. So suppose we have a point P in three-dimensional space, and if I want to describe its location in spherical coordinates, we are going to reference this green radial distance you see here. This is just the distance from our point P to the origin, and we're going to label that with the Greek letter rho. This is spelled R-H-O, and it looks like a P, but there's this curved tail here. Then we're going to reference this angle you see in blue, and this is just formed by the green line segment in the positive z-axis, and we'll label that angle with the Greek letter phi. And then down here we have our normal polar angle. So if I imagine projecting this green line segment down onto the xy plane, then theta is just the directed angle as we rotate from the positive x-axis to this yellow line segment. Okay, so now let's look at how we can relate these quantities rho, phi, and theta to the rectangular coordinates x, y, and z for the point P. So to start, just recall that in cylindrical coordinates, we have x and y in polar form. So x is r cosine theta, y is r sine theta, and z is just itself. So now in this figure here, I've gone ahead and labeled this yellow line segment with the letter r. This is just our normal polar distance. And then I've just copied that segment up here to form this right triangle, whose hypotenuse is the radial distance rho. And then if I look at the side opposite the angle phi, this is just the yellow line segment with length r. And then this adjacent side is just the altitude of our point P, and so it has length z. So now if I take the sine of the angle phi, I'm going to get the opposite side r divided by the hypotenuse rho. So put another way, r would be rho sine phi. And then if I take the cosine of the angle phi, I'm going to get the adjacent side z divided by the hypotenuse rho. So that will give us that z is rho cos phi. And so now if I replace r with rho sine phi in these polar equations for x and y, I'll get that x is rho sine phi cos theta, y is rho sine phi sine theta, and then from this equation we have that z is rho cos phi. And then we have these restrictions on rho, phi, and theta, namely that rho is a non-negative value, right? That's just describing our distance from the origin. The angle phi will be allowed to range from 0 to pi. So for that, you want to be thinking North Pole, South Pole. So if phi is 0, then I'm going to be up here at a point along the positive z-axis. And now if I think about fixing my radial distance from the origin and starting to increase phi, I'm going to start to rotate like this. And when phi is pi, I'm going to be down here along the negative z-axis, and you want to be thinking South Pole. Okay, and then we have our usual restriction there on the polar angle theta, just from 0 to 2 pi. Okay, so just a comment here about these angles phi and theta. If I imagine fixing a radial distance, okay, so think about moving along a sphere, and I also fix the angle phi and let theta vary, I'm going to be describing a circle of latitude on that sphere. Okay, so phi is really a latitude angle. And then on the other hand, if I were to say fix the angle theta, okay, and then let phi vary as I move along my sphere, I'm going to be describing a circle of longitude. Okay, and the historical names for these angles are zenith and azimuth. And if you've taken, say, astronomy, you probably would have seen these terms there. Okay, so now coming over here, there's another relationship I want to highlight, and that's that if you sum the squares of the rectangular coordinates, so x squared plus y squared plus z squared, you will just get the square of your radial distance rho. Now one way to see this is to simply square these expressions and then add them up and simplify using some Pythagorean trig identities, and while that would be all fine and good, there's a simpler explanation. the expression on the left is just the square of our distance from the origin. And rho measures our distance from the origin. So it makes sense that this left-hand side would just come out to be simply rho squared. Okay, so now let's look at question 6 on the worksheet. This says to describe each set of points given in spherical coordinates. And for part A, we're looking at the set of all points rho phi theta, where rho is equal to 2. Okay, so this is describing all points in three-dimensional space that are 2 units away from the origin. So put another way, we're really just describing here a sphere of radius 2 centered at the origin. And the fact that spheres are so easy to describe in this coordinate system is part of the reason why the system's referred to as spherical coordinates, right? So as I vary rho, I'm just going to be getting here a family of concentric spheres centered at the origin. Okay, so part B, it's the set of all points rho phi theta, where phi is equal to pi over 4. So I'm here fixing this angle in blue, okay, and then I'm going to let rho and I'm going to let theta vary. And if you give that some thought, that would be describing a cone, okay? So all points on this cone will form that angle of pi over 4 with the positive z-axis. And so again, I get a relatively simple description of this shape. Now in cylindrical coordinates, recall this cone would have had the equation z equals r, which is also relatively simple. In rectangular, it's a little more complicated. It's z equals the square root of x squared plus y squared. Okay, so that's quite nice. And then lastly, C, it says the set of all points rho phi theta, where rho is equal to 2 cosine phi. And here we're restricting phi between 0 and pi over 2. So this one, we're going to actually do a little algebra first. So looking at this equation, I'm going to go ahead and start by multiplying both sides of the equation by rho. So rho times itself will give us rho squared on the left. And then on the right, I'm going to get 2 rho cos phi. And now rho cos phi from right up here is just z. And from this relationship here in blue, the left-hand side rho squared then can be written as x squared plus y squared plus z squared. So this equation then becomes x squared plus y squared plus z squared is equal to 2z. Now subtract 2z from both sides and complete the square, and we get the equation x squared plus y squared plus quantity z minus 1 squared is equal to 1. Now this is the equation of a sphere whose radius is 1 and whose center is at the point 0, 0, 1. So think about taking the unit sphere centered at the origin and then just we're shifting it up, okay? Now, as far as this restriction on phi is concerned, okay, this is necessary for the reason that if you think about all points on this sphere, right, they're all living above the xy plane, except of course at the South Pole when I'm at the origin, right? So all these points on the sphere will correspond to angles for phi between 0 and pi over 2. Furthermore, if I plug in something, say, between pi over 2 and pi, I'm going to get a negative value for my cosine, which will I'll run into some problems here since I know that the radial distance rho has to be non-negative. All right, great. Well, that's a good place to stop. In the next video, we'll discuss how to set up a triple integral in spherical coordinates. Thanks.